Hi, it's Kristen Atchison, and we're going to be continuing our lectures on repeated measures ANOVA. So previously we've discussed how to calculate a repeated measures ANOVA, and you've had several chances to do practice problems. Just as is with a one-way ANOVA, we're still going to want to look at measures of effect size. We're still using eta squared for repeated measures ANOVA. The only thing that we're going to have to change is the denominator of our eta squared formula. It is still the percentage of variance that's explained by the treatment differences, and it's again it's what's telling us which variability that's not already been explained by other factors. So here are your formulas. Here is the practice answers from the study of fatigue and cognition. So you should have already done that. This is the F table and the ANOVA table from that study. And again, I just wanted to point out again that in these tables, that between subjects and error are additive to within treatments, and that's why they're set in a little bit on that table. Between treatments and within treatments are still additive to total. So again, just remember that relationship. So here again are our formulas. Using the data from that ANOVA table, we'll take that 840 for sums of square between treatments. We'll take 352, which is equal to sums of squared total, and we'll subtract 344 from that. We do that ratio, 840 divided by 352 minus 344, and we get 83%. Alternatively, we can also do this using the between treatments and sums of squared error. What we're going to do there is we're going to take sums of squared between treatments divided by sums of squared between treatments plus sums of squared error. So it'll be 840 divided by 840 plus 168. Either way, we still get 83%. So 83% of the variance is explained by the treatment effect, by treatment differences. So that's a really high percentage. So we have a really, that's a very good number to have. And the literature, again, we're going to have that same summary of descriptive statistics as we've had before with means and standard deviations. And we're going to still have that concise statement of the results. In this study, again, it was that, yes, there was an effect of fatigue as measured by time of night on cognition. There were more punished statements there were more punished statements as an effect of fatigue. Again, you'd want to include an F statement in that. This is an F statement for another study, F318. Again, it's important to tell us which F distribution we're talking about. That also tells us information about how many treatment groups there were and how much raw data we had as well. It gives us information about the samples we used. It gives us our F ratio of 16.72. It gives us our cutoff value. And again, if your alpha level, if you're able to reject the null and support the research hypothesis, if your F is in that critical region, you're going to want to include an effect size as well. And so this is where eta squared goes in your F statement. So this is, again, an appropriate F statement. Again, I like to include mean squared error in it as well because that allows you to build back an F table. And I just think that's very, very helpful. So I do that. Again, if I'm asking you for an APA statement, this one is fine. You don't have to include mean squared error. I typically will include it, but again, you're not required to by APA standards. Again, we're still going to have post-hoc tests for the same reason that we had post-hoc tests in one-way ANOVA. It's again, F is an omnibus test. It tells us there is an effect. It tells us fatigue was an issue, but it doesn't tell us that necessarily that the 6 a.m. was worse than the 9 p.m. It just tells us that there is a difference somewhere in there. Maybe they were actually, they had less punished statements as night went on because they were so tired. We don't know. By having that significant F, we just know that there is a difference. We don't know where. Again, we can determine exactly where those differences exist using these post-hoc tests. We can still use Tukey's HSD and Sheffey. We're just going to be substituting the sums of squared error and degrees of freedom error into the formulas as opposed to when we were using the mean squared within. We're going to be using that error because again, you're going to be wanting to use the same information that went into your F. So we're going to substitute that error and degrees of freedom error. And again, remember, we've taken the individual differences out of that sums of squared error. And so that's what we're going to want to use for these post-hoc tests. Again, Sheffy is still the safest, and you're going to want to use that mean squared error on the bottom of that formula. You're still going to have to recalculate that mean squared between just using the two groups of interest. Tukey's test is going to be the same. We're just going to substitute that mean squared error there as opposed to using the mean squared within. So again, both of those are the same test that we looked at with one-way ANOVAs, except we're going to be substituting that within information with the error information because, again, we've removed the individual differences from mean squared error. The assumptions of a repeated measures ANOVA are, again, very, very similar to what you've been experiencing before. Again, we want the observations within each treatment condition to be independent. Now, we know that they're not going to be independent across the person because we have the same person participating, but within each condition, we want them to be independent. The population distribution must be normal. Again, because we're basing all of these inferential statistics off of normal distributions, off of probability, they don't work if we're not dealing with normal populations. So again, because of the way these inferential statistics have been devised off of the normal curve, we need a normal distribution for them to be valid. And again, we should have that homogeneity of variance where we have very, very similar variance. Again, for the same reasons we want it with one-way ANOVAs. The advantages of the repeated measures ANOVA is, again, individual differences aren't affecting the outcomes. We're actually statistically, mathematically removing them from our F-test. We're taking them out. That's that whole step 2. And again, the same thing we had with repeated measures designs as a whole. A smaller number of participants is needed. You can get a lot more data out of 5 people putting them in all 4 conditions than you can out of 5 people putting them only in 1 condition. So again, we can use smaller numbers of participants. The disadvantages are, again, the same that we have with all repeated measures designs, that there may be these other effects, these other practice effects that are causing participants to change. Again, maybe issues of history, maybe issues of fatigue, maybe other kinds of order effects. All of those may be an issue. So we still have to concern ourselves with that with these ANOVAs when we're dealing with 3 groups, 4 groups, these multi-group designs. Those actually can become more of an issue than they were in just the 2-group designs with t-tests. So that wraps that up. Again, I hope you've already completed those practice problems. There's another practice problem available on D2L. From Dr. Good, so you can do the ANOVA and then go watch that hand calculation of that ANOVA for additional practice.